Hey everyone, today I want to talk about non-deterministic finite automata. Now, in order to sort of jump into this topic, I think what's easiest is to just build an example of an NFA and then explain what the differences between it and a DFA are. So let me go ahead and draw in an NFA and we're going to explain some of the key differences that we didn't see in the DFA case. So, like a DFA, an NFA must also include a start state. And the start state, remember, is represented by an arrow pointing into a state that originates from no other states. So this arrow pointing into this state here represents that this state is the start state. Now, an NFA also requires a finite number of states, right? It's called a non-deterministic finite automaton. So we need a finite number of states in our system. So let's go ahead and say that our NFA in this case is going to include 3 states, and 3 is a finite number, so that requirement is met. Cool. So we have a start state, and we have a finite number of states just like our DFA. Now we also require a set of accept states, and remember that accept states are denoted by these double circles. Now remember in the DFA formal definition that technically we could have 0 accept states, right? Because we can simply say that our set F of accept states is just the empty set, which is a subset of the set of states Q. However, that's not going to be particularly useful for us in a lot of situations because the only language that NFAs or DFAs can recognize if they have no accept states is simply the empty set. And that's not going to be particularly useful for us in pretty much every situation. So in most cases, we're going to want to include at least one accept state in our NFAs and DFAs. So let's go ahead and say that this last state here is going to be our accept state for our NFA. Cool. So we have a start state, we have our set of accept states, and we have our overall set of states Q. Now, also, like in the DFA case, we need to have a finite alphabet. So remember with DFAs, in pretty much every situation, our alphabet was just the characters 0 and 1, because the whole point of DFAs and NFAs and all these abstract models is that we're trying to model computers. And remember that computers can only read in the characters 0 and 1, or, binary. So like with the DFAs, we're also going to include the characters 0 and 1, but we're also going to include this other character called epsilon. And the reason that we're going to include this epsilon character will become apparent in just a second when we talk about the transition function. And technically, NFAs with this epsilon character thing are known as NFAs with epsilon moves. However, I'm just going to refer to this epsilon move thing or NFAs that have this epsilon character as just NFAs because NFAs with epsilon moves are equivalent to NFAs and they're basically the same thing. So I'm just going to refer to all of them as simply NFAs. So in this case, we are going to include this character epsilon in our alphabet. Now, the last thing that we needed for a DFA was a transition function. And we also need a transition function for non-deterministic finite automata. However, the transition function and sort of the requirements for the transition function are actually different in the NFA case. So I'm going to go ahead and draw in valid transitions for an NFA, and we're going to discuss sort of how they're different from valid transitions in a DFA. So I'll go ahead and draw in a transition on the character 1 here, transition for the character 0 here, transition for the character 0 here, and I don't know, let's also say we can transition on epsilon on this transition, and let's say we can transition on 0 here. Now, a bunch of red flags may already be, sort of springing up in your mind. Well, why do we have multiple transitions for the character 0 on one state? Well, it turns out that in an NFA, this is completely legal. In an NFA, we're actually allowed to have 0, 1, or multiple transitions for a single character on a single state. And remember that in the case of a DFA, that was actually not allowed. In the DFA case, we were only allowed to have exactly one transition per character per state. So that is one major difference between NFAs and DFAs. is we are now allowed to have 0, 1, or multiple transitions for a particular character on a particular state. Now, another key difference is this epsilon character here. Now, what exactly is epsilon representing? Well, if you recall from the DFA video and the regular languages video, epsilon represents the empty string, so the string with 0 characters. So essentially what this epsilon transition is getting at is that essentially we can take this transition by consuming no characters in our string. And just to make that a little bit clearer, let me go ahead and write an example string and process it a little bit, and we'll see how this epsilon transition comes into play. So let's say we want to process the string 0, 1. Okay, so just like in the DFA case, we're going to go ahead and start at the start state, right? Now, you may notice, well, there's no transitions for the character 0 on this first state, so what exactly can we do? Well, because we have this epsilon character here, we can actually take this transition by consuming no characters. So what we're going to do is we're going to start at the start state, and then we're going to take this epsilon transition by consuming nothing. So we're on the character 0, right? Well, we're going to go ahead and take this transition, and we're not even going to consume 0. So we're still on the character 0, but we're on this middle state here. And that probably seems really powerful right now. Like, whoa, we can move to a different state by not even consuming anything. That seems like it's going to buy us a lot in terms of, what languages we're going to be able to accept compared to the DFA case. And the crazy thing, at least to me, when I was taking my computer science theory class, was NFAs are actually equivalent to DFAs. And what I mean by equivalent is that if an NFA can accept a language, a DFA can also accept that language. So NFAs and DFAs actually have the exact same amount of computational power, which seems crazy, right? Like we have all these looser restrictions. We can be in multiple states at once. We can be in no state. We can like not even finish processing our string. We can take these epsilon transitions. It seems like we have all these options available to us that give us so much more power, but it actually doesn't buy us anything at all, which is kind of crazy to me. And something you may be asking, sort of given that fact, is well, if NFAs and DFAs are equivalent, why exactly do we care about NFAs at all? And the reason we care about NFAs is because, generally speaking, building NFAs is much easier and much simpler than building DFAs. So really the only reason, or I shouldn't say the only reason, I'm not an expert on this stuff, but the only reason that I've found that NFAs are really useful is that they're much easier to draw and build than DFAs. So that's why we're talking about NFAs. And in my next video, actually, I'm going to go over the equivalence between NFAs and DFAs and how we can translate an NFA into an equivalent DFA. So if you're curious as to how that all works, stick around for my next video as well. But for now, let's keep going with this example. So we've just covered how epsilon transitions work. We can take these transitions without consuming any characters from our string. Cool. So that is basically all of the main differences between NFAs and DFAs. We have these epsilon transitions, and we can also have 0 or multiple transitions for a particular character on a particular state. So now that we've covered the differences between NFAs and DFAs, let's go ahead and practice processing strings on an NFA because it works a little bit differently than in the DFA case. So let's go ahead and draw in just some sort of example NFA. Let's say this is our start state, and then we've got some sort of state up here. Let's say that we transition to it on the character 1. Let's say we've got our accept state over here, and we transition on the character epsilon. Let's say we loop on 0 here, and we can go to this state on 0 as well, and we transition to the accept state on 1 and epsilon. And like the last example, our alphabet is going to be the character 0, the character 1, and epsilon. Okay, so how exactly does string processing work on an NFA? Well, in the case of an NFA, because of the fact that there can be multiple transitions for the same character on the same state, we can actually end up in multiple states at once, or we can end up with multiple computation paths, essentially. So essentially, the condition for a string to be accepted on an NFA is that there needs to exist at least one path from the start state to an accept state such that the string finishes processing on that accept state. Cool. So let's apply that sort of definition of accepting a string to an example. So let's go ahead and try an example where a string is accepted. Let's say just the string 1. Cool. So it may look like, well, how exactly are we going to get to the accept state, right? We need to take like 2 transitions to get there, and we only have 1 character. Well, we're actually going to utilize our epsilon transition here to make this happen. So let's go ahead and start like we would in a DFA. We're going to start at the start state every single time we process a string. Now, we're at the start state, and we're on the character 1, right? So we need to take a transition associated with the character 1. And in this case, there's only one option, which is this top transition here that I'm circling. So let's go ahead and take that transition. Cool. So we've taken the 1 transition, and we're now at this top state here. And we've finished processing this 1 character. Now, you may be thinking, well, we've finished processing the string, and we've ended on a reject state, so we must need to reject the string, right? Well, in this case, that's not the case because we actually have a path to the accept state without processing any more characters, right? Because we have this epsilon transition. So because technically we finished processing this 1 and we're on this like empty character over here, technically this character could be represented as epsilon or just nothing. Well, because we have this epsilon transition, we can go ahead and consume this empty character or nothing and take this transition to the accept state. So we're on this top state and we've consumed nothing, and we're now on the accept state. Well, because we've ended on the accept state and we've finished processing all of the characters in our string, well, this string is actually accepted by the NFA. And again, just to be very clear about it, the reason why we were able to accept the string is because we took this epsilon transition from this top state and consumed no characters. And that allowed us to get to the accept state even though we finished processing this 1 character already. Cool. So that's an example of an NFA, excuse me, of an NFA accepting a particular string. Now let's go ahead and go through an example where an NFA does not accept a particular string. So let's consider, let's say, actually, I think this NFA might accept everything. Hold on just a second. Because if we have the character 0, okay, now. Okay, yeah. So an example of a string that this NFA wouldn't accept is the empty string, right? So let's go ahead and see why that's the case. So let's start at the start state, and well, we simply have the empty string, so there are no characters to consume, and there are no epsilon transitions on the start state, so we can't take any transitions, which means that we ended processing the string on a reject state, which means that we reject the string. So epsilon is actually rejected. Now, another example of a string that would be rejected would be, let's see, it could do 0, 1, 1. Yeah. So let's do the string 0, 1, 1 next. So let's go ahead and process the string on the NFA, and we're going to figure out why this string is rejected. So let's start at the start state, and we're currently on the character 0. So we need to consume this 0 character. Now, notice that there are 2 possible paths we can take. We can take the path to this bottom state and the path back to the start state. Now, technically what you want to do is you'd want to take both transitions and keep track of both of them. However, in this case, it's pretty obvious that taking this sort of starting transition isn't going to get us any closer to the accept state. So we're probably not going to need to consider that path. However, if we end up taking this other path and we're not able to get there, we'll also consider this other path and see if we can get to the accept state as well. So let's just consider this first path that actually gets us closer to the accept state, which is that we're going to take this 0 transition to the bottom state. Cool. So we've now consumed the 0 character, and we're now on this middle 1 character. Well, the only option we can take is we can take this transition on the character 1. However, we can also take this transition on the character epsilon, so we can consume no characters to get to the accept state. In this case, it's not really going to matter, so let's just consume the one character to make it easier. Cool, so we're now on this final one character. However, since we're on the accept state, well, there are no transitions on the accept state, so there's no possible way to consume this last one character. Now, because we can't finish processing our string, even though we're on the accept state, we are actually going to reject this string because we haven't finished processing the string. So any case where you get to the accept state, but you can't finish processing your string, that actually means that you're going to reject the string. Now, we said that we rejected this string, but technically there is another path that we could take. So before we say that, we're going to definitively reject this string, let's check the other possible paths. So this time, let's start at the start state, but instead of taking this bottom transition, let's actually take this looping transition back to the start state. So we're going to consume the character 0 and go back to the start state. And now we're on this one character. Now our only option is to take this upper one transition. So let's do that. We're going to take that one transition and move on to our next one. And we're now at this top state. Now, we only have one option from the top state, which is to take this epsilon transition. So what we're going to do is transition on epsilon, and we're going to consume no characters in our string. So we're going to remain at this one character, and this one is still going to be unprocessed. So we're going to take this epsilon transition to the accept state, but now notice that since the accept state has no transitions, there is no possible way for us to consume this one character. So even though we ended on this accept state, there are no possible ways to finish processing our string, which means that 0, 1, 1, or at least this path for 0, 1, 1 is rejected. Now, the only other path that we can consider is the path where we take this 0 transition and then we consume the epsilon character. However, this also isn't going to work because we're going to consume the 0 character and then consume nothing, and then we still have 2 1s to process, but there are no possible ways to process them, which means that that path is also going to end in a rejection. So because all possible paths lead to 0, 1, 1 being rejected, the string 0, 1, 1 is rejected by the NFA. So that's how string processing works on an NFA. Basically, for a string to be accepted, there needs to be a path from the start state to an accept state such that the string finishes processing on the accept state. And for a string to be rejected, there need to be no possible paths from the start state to an accept state such that the string finishes processing on that accept state. Cool. So that is how you process strings on an NFA. Next, I'm going to go over a quick example of how we can build an NFA to recognize a particular language. However, I'm going to go over it a little bit more quickly than the DFA video, just because we've already sort of done the DFA case, and the NFA case is pretty similar. So let's say that our language is the set of strings 0, 0, and 1, 1, and our alphabet is the character 0, the character 1, and the character epsilon. And we want to build an NFA that recognizes this language. Now, just like in the DFA case, there are a few things that we can guarantee in our NFA. One, we know that our NFA must contain a start state. So let me go ahead and draw that in. We're going to have our start state here with our arrow pointing into it. Perfect. So we now have our first state figured out. However, something else we can also determine is the fact that since the empty string is not in our language, as you can see down here, well, that means that our start state needs to be a reject state, right? We went over this in the DFA video as well. But if we start processing on the start state and we're processing the empty string, well, if the start state is an accept state, then that means we're going to end processing epsilon on an accept state, which means that it's going to be accepted. And because epsilon is not in our language, we don't want that to be the case, which means that our start state must be a reject state. Cool. So now that we've got those two things figured out, we sort of have to actually do some thinking to get the rest of this working. So a strategy that I like to employ when building NFAs and DFAs to recognize some language is I like to try moving towards an accept state if we read in characters that get us closer to a string in the language. So my first instinct on this problem would probably be, well, let's transition to a closer state, to an accept state, if we read 0 or 1, right? Because if we start at the start state and we read in a 0 or a 1, well, we've gotten closer to either the string 0, 0 or the string 1, 1. So let's move to a state that's closer to an accept state. And while I think that's a good intuition, in this case, it's actually not going to work out very well for us. And the reason why is because this next move, or whether we move to an accept state or not on this next transition, depends on what the previous character was, right? Um, like if we read in a 0 and we read in a 1, well, we're actually going to reject that string. But if we read in a 0 after our previous 0, then we want to accept it. So essentially what I'm getting at is that whether or not we accept the string from this point depends on what the previous sort of path was. It depends on whether we took this 0 path or this 1 path. So what I would recommend is splitting these paths into two separate paths in our NFA so that we're keeping track of what the previous character we read in was. So let's go ahead and do that. So instead of having just one transition for 0 and 1, let's have a transition for 0 that goes on this path, and let's have a transition on the character 1 that goes down on this path. So now, if we ended up on this top state, we know that the previous character we read in must have been a 0. So we're keeping track of what the previous character was. And the same thing goes for this bottom transition. If we ended up on this bottom state, we know we must have just read in the 1 character. Cool. So now that we're keeping track of these separate paths, what exactly is the condition that's going to get us to the accept state? Well, let's first consider the top path. So if we're on the top path, or if we're on this top state, that means we just read in a 0. So the only way to get 0, 0 out of this is if we read in another 0. So let's draw in a transition to the accept state on 0. Cool. So that covers the top path. And you may be thinking, well, hold on, where's the 1 transition for this state? Well, remember what we just talked about. In an NFA, we do not explicitly need a transition for every character in the alphabet on every state. So we don't need to actually include a 1 transition on this top state here. And I guess you may be asking, like, well, what's the reason why we wouldn't want to include it? Well, if we don't include a 1 transition on this top state, well, if we move to this top state and we have a 1 character, then since no transitions exist for the 1 character, we simply just stop processing the string and the string is rejected. And that's exactly the behavior we want. If we read in a 0 and then a 1, we know for a fact that our string cannot be in the language and we want to reject it. So that is the desired behavior. Cool. So we can actually apply the same logic for the bottom root. If we're on the bottom root, that means that we just read in the 1 character, which means that the only way to get to the accept state is if we read in another 1. So let's go ahead and draw in a transition for the 1 character here. And again, we're going to leave out a transition for the 0 character, because if we read in a 0 after a 1, we know that the string cannot be in our language, so we want to reject the string. Awesome. And this is actually going to be our completed NFA. This NFA recognizes the language L. And just to sort of convince you of that, let's go ahead and process a few strings on our NFA and make sure that it lines up. So let's first test the strings 0, 0, and 1, 1 and ensure that they are accepted by the NFA. So let's start by processing the string 0, 0. And I'm going to go through this pretty quickly, but I am going to explain it thoroughly enough so that we understand how it's working. So remember that for a string to be accepted on an NFA, there must exist at least one path from the start state to an accept state, such that the string finishes processing on that accept state. Okay, so let's go ahead and process it and see if that's the case. So we're going to start at the start state. We're going to take in the 0 character and move to this top state here. And then we're going to take in the second 0 character and end on the accept state. Now, because we finished on an accept state and the string has finished processing, we say that the NFA has accepted this string. Now let's go through the 1, 1 string, because this string should also be accepted. So let's start at the start state. Let's take this bottom transition on the character 1, and then take this next transition on the character 1. And that's going to get us to an accept state, and we finish processing the string. So that means that 1, 1 is indeed accepted. Cool. So now let's try two examples where the string is rejected. Let's try, first of all, epsilon, because that's usually a good edge case to test, rather. And then let's test 0, 1, because this should also be rejected. So starting with epsilon, well, we're going to start at the start state. And while there are no epsilon transitions, so that means we're just going to stay right here at the start state. And because the start state is a reject state, that means that we reject the empty string, which is what we want. Cool. Now let's finally finish with 0, 1. So let's start at the start state. And because our first character is 0, that means we have to take this upper transition. So let's take the upper transition to this upper state here. And well, now since our next character is 1 and there are no transitions for the character 1, that means we cannot finish processing our string and the string is rejected by the NFA. So 0, 1 is rejected. Cool. So that is how you build an NFA to recognize a particular language. It's pretty much the same as with the NFA case, and with the DFA case rather, but I actually think it's easier than the DFA case. And the reason for that is because we have much looser restrictions on how we can draw our transitions. And I feel like in a lot of cases that leads to a much easier time building these things. Cool. So that is our example for building NFAs. And finally, I want to go ahead and go through the formal definition for NFAs. Okay, so our definition for an NFA is actually going to be almost exactly the same as a DFA. The only difference is going to come in our transition function. So let's start off by saying an NFA is a 5-tuple Q sigma delta Q naught F. And I don't think I used this terminology in the DFA video, but all a 5-tuple is just a collection of 5 things. So this first part is basically saying an NFA consists of these 5 things right here, Q, sigma, delta, Q naught, and F. So we're going to say an NFA is a 5-tuple Q, sigma, delta, Q naught, F consisting of, and we're going to go ahead and define these 5 things. So it consists of a finite set of states Q. And remember that this is the same as the DFA case, right? A DFA must also contain a finite set of states Q. And then second, we need to define sigma. So our NFA also contains a finite alphabet or set of input symbols, sigma. And this is again the same as the DFA case, right? We had a finite alphabet sigma in our DFA as well. And now this is where our NFA is going to differ. We also need a transition function delta. And the only difference in the transition function is that our codomain is going to look a little bit different. And I'll explain why the codomain is the way it is after I define this function here. So delta needs to have domain Q cross sigma. And that's exactly the same as in the DFA case, right? We're mapping state character pairs to something else, which means that our domain needs to be the set Q cross sigma. Now, our codomain, instead of being Q, is actually going to be the power set of Q. Now, why exactly does this power set of Q codomain thing allow us to have those like multiple transitions or 0 transitions for particular characters? Well, recall the definition of the power set. The power set of a set is simply the set of all subsets of that set. So for example, if we had the set 1, 2, and we took the power set of that set, well, that's simply going to equal the set of all subsets. So it'll contain the empty set, because the empty set is a subset of every set. It'll contain the set containing 1, it'll contain the set containing 2, and it'll contain the entire set itself, so the set 1, 2, because every set is a subset of itself. So this is the definition of the power set. It is the set of all subsets of a particular set. So the reason why this power set thing allows us to have multiple transitions for the same character is because, well, let me actually go ahead and write out the power set of Q, and we can see why that's the case. So let's say that Q contains 3 states. So we'll say, actually that's going to take a while to write out. Let's say that Q contains 2 states. So we'll say that Q equals Q1, Q2. Well, what's the power set of Q? Well, the power set of Q is the set containing the empty set, the set containing, it should have Q1, and then we need the set containing Q2, and then finally the set containing Q1 and Q2. Come on, pen work. There we go. Okay, cool. So here's our power set of Q. It contains the empty set Q1, Q2, and Q1 and Q2. So imagine we want to have a transition from Q1 to Q1 and Q2 on the character 1, which is something we can only do in an NFA. Well, in order to represent this, we can say that we can map the ordered pair Q1, 1. Well, we can go and actually map this to, well, we can map it to one of these sets in here. So if we want to map Q1 and the character 1 to both the state Q1 and Q2, we're going to actually map it to the set Q1, Q2. So this is actually what allows us to have multiple transitions for a single character, is the fact that because we're using the power set, we have every single possible combination of states at our disposal. So we can go ahead and map any state character pair to any subset of states we want. So this is basically saying that on the state Q1, on the character 1, we can either move to the state Q1 or the state Q2. So that is why having the power set as the codomain allows us to have multiple transitions. Now, the reason why we're able to have no transitions for a particular character is because we also have this empty set, right? So we can actually map any state character pair we want to the empty set, which basically represents, well, on the state Q1, on the character 1, we're mapping to no state. So there's basically just no transition that exists for this state character pair. So that is why we use the power set in the codomain in our transition function for the NFA. Cool. So we've now sort of talked about our transition function, and everything else is going to be exactly the same as in the DFA case. We still need a start state Q naught in Q and a set of accept states F, which is a subset of Q. And this is our full definition of an NFA. We need a finite set of states Q, a finite alphabet sigma, a transition function delta from Q cross sigma to the power set of Q, a start state Q naught in Q, and a set of accept states F such that it's a subset of Q. Cool, so that is a brief overlook on non-deterministic finite automata, and in the next video I'm going to go over DFA and NFA equivalents and how we can translate an NFA into an equivalent DFA. Thanks for watching.